Oh, I started the recording without really actually starting the PowerPoint. This is the last laboratory that we have in this section, Lab 32, the control of breathing. This is only from the supplement. And this is really simple lab. You can actually do it at home if you feel like experiencing it would certainly help. And the idea is to measure breath holding time under different conditions. If you do it yourself, just be safe and don't pass out or anything. But here's what we're going to do for this one. Because it's fairly simple, we're going to combine the introduction and the discussion together and take a look at some of the aspects of it. Of the three labs on this section's exam, Lab 27, Lab 25, 26, and this one is by far the simplest and will be the least representative, but you still should understand it and know it. So the objectives for us are to examine what happens by changing variables in terms of your breath holding. And one of the things we're going to look at is what's the effect of changing the volume of air in your lungs on your breath holding time. And we're also going to look at the effect of changing the status of your blood gases, um, especially as related to the carbon dioxide, as we'll see. And we're going to look at whether it's a lack of oxygen or an increase in carbon dioxide that is the stronger drive to breathing. So what really controls respiration? And I think most of you, if you think back to lab 2, should be able to figure out it should be CO2. So some general procedural notes that we would have everybody hold their breath until the same level of discomfort each time. We would make sure it wasn't a competition, so nobody really cares how long you can or can't hold your breath for. And, so don't cheat in order to get a longer time than your lab partner. And as I said before, you're not allowed to pass out either. What we would do is we would determine the breath holding time under 6 different conditions. We'll go through these conditions individually, so I won't go over them now, but you can see them down here. And for the exercise, we wouldn't do in the classroom because it's just too loud. What we could do if we went outside is everybody could run in place and then hold their breath um, after doing that for about a minute. But if we try to do it in the classroom, it just sounds like you're having an earthquake and everybody in the building freaks out. So let's kind of look at each one of these conditions and talk about what's happening. So the first 3 conditions that we're going to look at, kind of because they're similar, is the maximum inhalation. So you just be breathing normal and then take a maximum breath in. And we'd record breath holding time. We do it individually. That's this first column here. And we do it as a class average. This is the second column here. So we'd have everybody put it on the board. Then we do, after a brief interlude, normal inhalation. So you would just be breathing normally, and it's kind of hard to do because you're not used to it, but then you would just take a normal inhalation and hold your breath for as long as you could. And there you can see the breath holding time was less for both the individual and the class. And then what we would do is we would do a maximal forced exhalation. So you would blow out all the air you could from your lungs. Now remember from the number 26, 25, 26, that you cannot blow out all the air out of your lungs. You have that residual lung volume there, and it's there for a couple reasons that we mentioned in 25, 26. So even though you try to blow out all your air, you're still going to have some left, which is good, right? And so we'll kind of look at those different conditions and compare them. So one of the things you can easily see, and again, we don't look at the individual time, although it mirrors the class average somewhat. The longest time was maximal inhalation. So when we had a larger lung volume, we have a longer breath holding time. When we had a normal inhalation, that's a middle of the road lung volume. And then when we forced all of their air out, that maximal exhalation, we had the lowest time. So as we can see from the class, and this is, these numbers sometimes are a little higher, a little lower, but this trend we see in every class every time. I've never not seen this with literally thousands of students. I've done this in the past. for class average, to figure out the class average, we see that as the lung volume decreases, the amount of air that you have in your lung decreases, then the breath holding time decreases as well. Okay, so that's one of the take-home lessons. You probably knew that already. It wasn't like if I said, hey, let's have a contest to see who can hold their breath the longest, you're going to all of a sudden blow out all your air and try to win, right? So the question then is, all right, our conclusion down here, right, is if our time that we can hold our breath is proportional to the volume. The more volume we have, the more hold time we have in terms of the breath holding, right? There are two things that happen when we're experiencing our breath holding and have that change in lung volume. In the one case, we start with more oxygen, right? So you could argue very easily that, hey, I've got a bigger lung volume after maximal inhalation. I have more oxygen, therefore I can hold my breath longer. The second thing you could argue would be, oh, wait a minute. Our metabolism's the same because we're just sitting there resting when we're holding our breath. So there's no difference there. But what's happening is that I am producing CO2 at the same rate. And when I have a smaller lung volume, there's less space for my CO2 to go into. And so the CO2 builds up quicker. So essentially, I have a higher CO2 value when I have a smaller lung volume. So you could argue it's the CO2 that happens when you have a larger lung volume. You have less CO2, so you can hold your breath longer. And basically, all we can tell from this experiment, the way we've done it for the first three conditions, A, B, and C, that the bigger the lung volume, the longer you can hold your breath. As an extension of that, let's say that you got hooked up to the respirometer that we've seen before, right? One of the things you could easily note would be in your respirometer, you would have a bigger lung volume, and if you tried to hold your breath in the respirometer, you could do it much longer because you had a much bigger lung volume. But the question would be, which is the right reason? Is it the oxygen? Is it the CO2? Or is it a combination of both? Which is the stronger condition that drives ventilation? And so we have to do some further experiments to see that. So what we're going to do is a couple little experiments. D and E are really the two big ones that do this. F is a little different because it changes the metabolism. But D and E are done sitting. So in D, we would, instead of hyperventilating, we would just take 2 or 3 deep breaths. And what that does is it gets rid of the arterial CO2. So it causes the partial pressure of CO2 in your blood and in your lungs, actually, to go down. It doesn't change the arterial oxygen. The arterial oxygen, we have a couple pulse oximeters in the lab, and we usually, have a couple volunteers. So there's like 4 or 5 students wear them. And we see that the oxygen saturation measured as the pulse oximeter is 99%. It doesn't change, right? And it's already 99%. You can't get any higher than that anyway. And so when we see people that do these deep breaths, it's similar to hyperventilation, but you don't have the same issue you would have with the increase in metabolism we saw way back in lab 2. So they would just take 2 deep breaths in, just like that, and then they'd hold their breath. And invariably, that breath holding time goes up. Since we're looking at the deep breathing, right, we actually have the wrong column up here. We should be comparing it to maximal inhalation because that's what you do after the deep breaths. And the class average was 58. So if we look here after 2 deep breaths, the class average goes up to 72. So it significantly increases, right? That's, almost 20% in terms of breath holding time. Remember, this isn't just one person. This is the class average. So it's, probably 25 people or so each class. So we see that in D, we decrease the CO2. The oxygen doesn't change, right? So in D, we decrease the CO2. Hang on a sec. So here, we decrease the CO2, right? But the oxygen is the same, right? So I'm going to change the color. We'll use this weird green and say the O2 stays the same, right? So the argument would be if it was oxygen that drove ventilation and oxygen didn't change, breath holding time shouldn't change. But if it's CO2 that drives ventilation and CO2 goes down, we should have an increase in breath holding time. So remember, the class average, right, for the maximum inhalation, it's hard to write, but was 58. So we'll look at that. So it doesn't prove anything, but it definitely is consistent with the idea it's CO2. So E, what we're going to do is we would do rebreathing. What we would do is in E is we would have the person, actually the entire class, breathe together into a paper bag. They all have their individual paper or plastic bags, but you would breathe for about 2 minutes. So I would time the class, we'd breathe, and what you're doing is you're rebreathing the CO2 that you're expiring. When we breathe air from the room air, there's very little CO2 in it. It's literally 0.04%, right? So it's 0.4% in the room air we breathe. But if you breathe into a bag, that increases the CO2 concentration, and it might go up to 3 or 4, even 5%. So then after the 2 minutes, we don't do it that long. We don't want to change CO2 that much. You would take a maximum breath in from the bag, from the air you breathe. And studies show, and again, for a bunch of reasons, that the oxygen stays the same. So I'm going to do it here again. So oxygen stays the same here. And, the pulse oximeters in class still say 99% all the time. I've never seen it change. And then the CO2 in this case, right? CO2 goes up. And the reason it goes up is because you're now, instead of breathing room air that's got virtually no CO2 in it, you're breathing air from the bag that has 3, 4, 5% CO2 in it. So the idea would be, again, if it was oxygen that drove ventilation and oxygen didn't change, then breath holding time shouldn't change. But if it was CO2 that drove ventilation and we started with more CO2, that should result in less time for breath holding. So if we look, right, we see that originally without doing anything and just taking a maximum inhalation, it was 58 seconds, right? There's our 58. When we had deep breathing and we had less CO2, so less CO2, right? We had 72 seconds. And then for rebreathing through the bag and we have more CO2, we have 32 seconds. So in all three cases, oxygen didn't change, but breath holding time changed significantly, and it changed exactly in the manner you would expect it to be if it was CO2 that drove ventilation. And so the conclusion of the two experiments, the deep breaths, which basically is hyperventilation without the increase in metabolism, that decreases CO2, and the rebreathing that increases CO2 without changing oxygen. If you do it long enough, you're not going to change oxygen. We have more than enough oxygen in our room air to breathe. It's probably not until you get up to what is the equivalent of about 3,000 feet of altitude where the oxygen actually starts to affect the oxygen that gets into our blood. But breathing through a bag for 2 minutes doesn't get there yet. So it's still totally normal in terms of oxygen. So that's a really good thing to kind of look at. And in the conclusion, which we'll put down here, right, is CO2 drives ventilation. Okay. So CO2 drives ventilation. That's the big one. And the evidence for that, right, is E, because we increased CO2, didn't change oxygen, and breath holding time went down. And D, because we decreased CO2, didn't change oxygen, and breath holding time went up. All right. The other thing then is, CO2 is inversely proportional to breath holding time. The more CO2 we have, the less we can hold our breath. So that's kind of the big take-home lesson for there. For exercise, and if you exercise, next time you exercise and you're just done, when you stop, you don't even have to do anything different. Just try to hold your breath. And what happens is, because of the increase in metabolism, it's very, very difficult to do that. And, most people can do it just a couple seconds. Depends on how hard you're exercising, obviously. We're not going to worry about that for the exam purposes. So that was what we're looking at for the CO2, and especially is related to letters D and E of this exercise. Okay, so that was the last slide, and that's why I said, we'll just do it together, both the data collection and why we did it. But just a quick review then. The two big take-home lessons from this experiment were that as we increased lung volumes, we increased breath holding time. And as it's CO2 that drives ventilation. Oxygen plays a role when it gets really low in most people, and sometimes to such a low degree that you could run out of oxygen and pass out before your body said it was time to breathe again because of the CO2 increased. You see sometimes when someone hyperventilates very vigorously, they can do that, and they can get rid of so much CO2 that the CO2 doesn't build up high enough when they hold their breath to tell them they have to breathe, but the oxygen sensors are relatively insensitive, and it doesn't tell them, hey, they have to breathe, and they can run into problems. And occasionally people drown because of that. A couple of years ago in Oakland, a child unfortunately drowned while doing that, and Oakland's response, which probably was maybe a bit of an overreaction, but decided that nobody could hold their breath in swimming pools anymore, in the public swimming pools. So it can happen, and just be careful with holding your breath, but make sure you understand that the two things we have and what the evidence for that is. So A, B, and C, the different lung volumes show it's the lung volume that affects breath holding time. Bigger lung volumes, bigger breath holding times. And then D and E were the experiments, the deep breaths and the rebreathing through the plastic bag changed CO2, didn't change oxygen. And we saw that it's CO2 that drives ventilation, because when we increased CO2 with rebreathing in the bag, breath holding time went down. And when we decreased CO2 with hyperventilation, the deep breathing, then breath holding time went up. So that's lab 32, and that's the last lab on lab quiz 4.